So let's just give a quick recap of the Rayleigh criteria. So Rayleigh criterion is a basis by which we can say whether the two objects are separated or distinct or they are still the same. So what he said that every point object. So when you try to see a point object through lens or through whatever optical instrument, the point object creates a diffraction pattern. So a point is not creating a point, isn't it? So a point creates a diffraction pattern with one big central bright fringe and then some concentric dark fringes. Okay. And then concentric bright fringes. So it will have some rings like this. If I take another point object, which are very close to this, the first particle or first object, then it will also create its own bright fringe, and because it is slightly, you can say, up or down, so it will also having some position like this, or maybe like this. So this bright fringe, and it will have some concentric bright also like this. So what Rayleigh said that the two objects are said to be resolved if the first minima of the diffraction pattern of the first particle falls on the where center of the central maximum of the second particle. So what is the condition? So I'll mention this here. Two images. See, we resolve images, not the object, right? We resolve images. Two images are said to be just resolved. So two images are said to be just resolved if first minima of one of the particles it's better to say the particles diffraction pattern falls on the center of central maxima of second particle's diffraction pattern or vice versa. So two images are said to be just resolved if the first minima of one of the particles diffraction pattern falls on the central maxima of second particle's diffraction pattern or vice versa. Okay.
Yes, sir.
If you draw something like this, so I think I have written this criteria already, right? C1, C2 and all, correct?
Yes, sir, the drawing.
Yeah. So if the radius of the central bright fringe, if I say R, let R be the radius of central so if R be the radius of central bright fringe, then if C1, C2 equals to R, we say just resolved less than or unresolved fully
Okay, sir.
I hope this is clear.
Yes, sir.
Now I talked about the resolving power of telescope and microscope. So we know that in case of telescope, can we really see the actual separation of the two planets or stars? The answer is no.
No, sir.
So in case of telescope, we talk about the angle which it subtends. So we talk about the two nearby star. So think this way. So resolving power of telescope. Okay. So in case of telescope, so we have a lens, and the lens will act as a opening, aperture, or whatever you can name it. Okay. So this is like a slit, but it's a circular slit, right? Or circular opening. Okay.
Yes, sir.
So I am going to going to take the diameter. We will keep as A itself without changing the formula. In textbook, the assumption will change. So they might take a two-way somewhere in NCRT. They have taken two-way, but I would like to stick to the single slit assumption or the variable name. So I'm keeping it still A. But now here A will represent the diameter.
Yes, sir.
And now we have a screen here. So we'll see what exactly happens. So think about two stars. Twinkle, twinkle, little stars. We have the first star. And imagine the when the light coming from the first star passes through the slit, it creates a diffraction pattern, as we know, right?
Yes, sir.
I'm doing that something like this. It's actually on the plane, but I'm just flipping by 90 degrees and showing it to you. Okay.
Okay, sir.
So it is basically like this. It's not here. It's something like this in the plane. What I mean to say, it's like this way. Here it is. Okay.
Yes, sir.
Okay, let me try to create a 3D visualization. Maybe the perspective will be better for you. So what really matters is the perspective, right?
Yes, sir.
Okay. So the star will cast its image as a diffraction pattern. And this is the first, I'm just showing the central battery, not the next one. Okay. Now,
Okay, sir.
if you consider immediately the closest star, so you can have many closest star. But the thing is, if the stars are really close, and if their diffraction pattern is something like this, we won't be able to say that these two images are resolved, right?
Yes, sir.
So some distance is required to make this main. So I'll just draw another star, and this star will send its beam of light like this. Okay, I'll make it. I'll change this as well. I need to match the requirement.
Okay, sir.
So this is my second star, and these two stars obtain some angle on the. This is called objective. Why objective? So in case of human eye itself is the objective, right?
Yes, sir.
And the screen will act as retina if you want to correlate,
Yes, sir.
depending on if it is in the because the light ray coming from the star will be coming from infinity. That's the whole idea. And any beam of light coming from infinity will get focused on the focal plane of the lens. So this distance we keep as f. And this f represents what? Focal plane of lens, focal length of lens. Now you may be asking why, because the beam will get focused at best in the focal plane, right?
Yes, sir.
Okay. Now the another star will create its own diffraction pattern, something like this. And what we wanted that the center of the one of them should fall on the first minima. Correct. You can see the pink is the center of the pink is falling at the center of the at the periphery of the first one, right?
Yes, sir.
So that's the first minima.
Yes, sir.
So if I call this angle as d theta, this we can also call it as d theta, right?
Yes, sir.
And we know this is r. Okay. So we can add d theta equals to r by f. Simple relation.
Yes, sir.
Now we know how to find r. For that we need to go back to the. So for r we can think of the condition for minima. Condition.
Sir, can you just come back in a second?
Yeah.
Sir,
Yeah.
yes, sir. Sir, sorry for the delay. Winter started here and it was super cold in that room.
You're fine.
Okay, sir. Sir, your voice is a little low.
No, I'm not saying this. No, not saying. Okay. All right. So, so we got the G equals to 1.23 lambda by, where A is the aperture. Mind you that symbolically, the A may appear as diameter sometime, the A may appear as radius sometime, depending on the author. They can prefer their way of assumption. So when you solve question in the examination, think A as the aperture diameter. Okay,
Yes, sir.
which means aperture. Now d theta is this much, which means this is the minimum angle at which two stars can be seen distinctly by the human eye. Understood?
Yes, sir.
So the inverse of resolving limit is called resolving power. So the power is simple. So power is inverse of limits. We can add 1 by d theta. And this angle turns out to how much? It is
122 lambda.
A by 1.22 lambda, right?
Yes, sir.
So this is the power. Okay. So they may give you that for a given wavelength, if this is the power, then find the A, find whatever. So yeah, it's good to solve some question of this power. And let me finish the RP of the microscope, then we go further. Okay.
Yes, sir.
So there is also called something called Fresnel distance. Fresnel's distance. So we know that for single slit diffraction, for minima, A sine theta is lambda, n lambda. So for first minima, A theta equals to, you can say a small angle, you can just write it the way you want. So you can say, let's say A d theta equals to lambda, or just simply you can say A theta equals to lambda, doesn't matter. So in that case, the R is how much? The width. You can say R only. Yeah. So So what I'm trying to say is that okay, let's keep it circular only. But there is an approximation. I mean, the way it is explained is for I tell you. So Fresnel distance. So we know that R is how much? 1.22 lambda by A, if you
Lambda by
remember.
A. Yes,
Okay.
sir.
So sorry, into F for F, right? Now imagine if I perform the same experiment. So if I take this distance as Z, so what will happen that we know the first minima will form at by the condition that if I say this is theta. So we know that A sine theta or simply A theta is 1.22 lambda. This is for circular aperture, right?
Yes, sir.
So now if I talk about this length, this R, how big is the R? So we can say R equals to Z theta, correct?
Yes, sir.
So Fresnel distance is taken. So if this is Z theta, so Fresnel distance is the distance at which the size of the image is equal to the aperture size. So if I want to define it, it is the distance at which it is the distance at which size of central bright fringe equals to aperture size. Okay. So here size means the radius actually. So we take R equals to, so if this is equals to A, then what do we call? The distance, the R, so the value of R if becomes A, then we call Z as the Fresnel distance. This Z is called Fresnel's distance. So the way of writing is Z theta equals to A, and theta we can write as how much? Lambda by A, right? And
Yes,
one
sir.
point, see now there is some clever trick. So they don't take 1.22. They just keep it A only, ignoring factor. So this is a rough approximation. So Z equals to how much? A square by, yeah. So this is the approximate value that they have taken. Okay.
Okay, sir.
All right. So this is called the the way it is derived in the textbook, I mean, if you talk about the derivation, I think slightly different and change the sign. Just am I audible now?
Yes, sir.
Yeah, so this is the formula. You have to just remember the formula. So this is called the fractional distance. Now, why this distance is important? So the validity of ray optics. The validity of ray optics is only for the fractional distance. If the distance is more than fractional, the diffraction will be a prominent feature, so ray optics will not validate. So the
Okay, sir.
purpose is this is to validate the validity of ray optics is valid for distance d such that d is less than fractional distance. Okay, so this is something just you need to remember.
Okay, sir.
The next is resolving power of microscope. So in this case, we do not talk about the infinity and all. It's in microscope, the object, the specimen is kept at a very close distance, some finite distance, right?
Yes, sir.
So how we design actually is this. Now there are some rules that we need to understand. The first rule is uh, while creating the microscope, the object must be kept beyond the focal length of the lens. Otherwise, it will form the virtual image, right? So what we want is that object is on this side, the image must be on the right hand side, right?
Yes, sir.
So our object will be here, and the distance that we choose or we call this is called u. And the image we obtain will be at v, because for u there is a v, for u there is no f, right? For infinity it is f, isn't it?
Yes, sir.
So let's say u is the object distance and v is the image distance. So what will happen is it will form the diffraction pattern. Let's do this. So this is the diffraction pattern of the first object. Okay. The
Yes,
next
sir.
object, we have to keep it very close, and it will form its own diffraction pattern. And again, what we want the same condition, Rayleigh criterion to be met. Okay. So yeah, you want to say something?
Sir, no, sir.
Okay. Now this separation is the minimum distance. This is the d minimum, which can be seen distinctly, right?
Yes, sir.
So if this is the d minimum, so we can take a d minimum as the height of the object. Then the r will act as height of the image, isn't it?
Yes, sir. Sir, are you able to hear me?
Yeah, I can hear.
Okay, sir.
So the relationship that we can find if this is theta, not this is theta, so this is alpha. So theta here is something important to designate, so we'll call it alpha. So if
Okay,
this will the center of the two images will act as the image of height of image, and this will act as the height of object. Okay.
yes, sir.
And from the magnification, we can say that height of image upon height of object is V by U, isn't it?
Yes, sir.
Okay. And the height of image we can act as V theta, V alpha, right?
Yes, sir.
So V alpha by H object, because that's known to us, is V by U. So the height of object turns out to be how much? U alpha,
Mhm. Yes, sir.
am I right?
Yes, sir.
Okay. But this is not we want to write here actually. We don't want to write here. So okay. Let's keep this. Let's just okay. Fine. So what we are really looking for is the D minimum. So how to relate the D minimum? So you can see that D minimum is U alpha, but alpha we know. Oh, sorry, that's fine. So D minimum is how much? It's a U alpha. That's simple.
Yes, sir.
Nothing wrong about it. Just use. And alpha is how much? It is angle of the first minimum, which is 1.22 lambda by A.
Mm,
A sine alpha is 1.22 lambda for first minima,
yes, sir.
isn't it?
Yes, sir.
So okay, we got the answer. So we got D minimum equals to U into 1.22 lambda by A. Okay. Now this is the answer, but we have to express this in a different way actually. So there is something called numerical aperture. So I'll talk about this. What is this? So it is the maximum angle up to which the light can enter the lens or the aperture. So this angle we call theta, which is the maximum angle. Okay. And because this is A. This is A. So we can write as tan theta equals to how much? A by 2U,
Mm,
correct?
yes, sir.
So U, because we want to replace U, so U becomes how much? Because we don't express answer in terms of U, rather we express answer in terms of theta, which is the maximum angle at which the light can enter. Okay. So
Yeah.
U turns out to be how much?
Mm. So 2 tan theta by A.
A by 2 tan theta.
Oh, right. Yes, sir.
So if I call the question, if I call the question one from 1 and 2. So this is how we express it. So the rule is we always express in terms of this one. So we can write from 1 and 2, D minimum equals to A by 2 tan theta into 1.22 lambda by A. A gets cancelled, right?
Yes, sir.
So what we get is so what we get here is D minimum equals to 1.22 lambda by 2 tan theta. 1. And this you can write as 0.61 lambda by tan theta. And because size the aperture is very small, so sometimes we can replace this by sine theta also. So we replace this by 0.61 lambda by when theta tends to 0, right? For a small angle, you can write this like this.
Yes, sir.
So this is the formula that you will see as the D minimum formula. Okay.
Okay, sir.
But there are some ifs and buts. So what happens if I bring a medium into picture? So let's say if the medium on both sides of the lens is not same. So things will change a bit if I bring a medium into picture.
Mm,
Let's say if I bring mu on this side, then this is D minimum, right?
Yes, sir.
And so what happens? The ray of light from here to here will change. So this will not be same angle. Okay. So if this is alpha, this will be beta actually. It won't be same. Understood?
Yes, sir.
It won't be same. So the question is how to relate the angle alpha and beta. This remains theta.
Sir, will it be like the refracted angle?
Yeah, correct. So we have to write that one. So it's a mu1 sin 1 equals to mu2 sin 2. So the way of writing will change. This is sine theta pretty much. So we write as a mu1 sin beta is equals to 1 sin alpha, right?
Yes, sir.
So basically, you can also write as tan beta. I mean, it really doesn't matter. So tan beta equals to sin alpha. So the formula will change a bit. So this will become D minimum by U. Okay, I haven't mentioned this U and V again. And then sin alpha you can write as HI by V, right? So what you can realize that and HI we know how to find. HI we know how to find. So HI is alpha into V. So this
Yes,
means this is always alpha. But now the D minimum will be how much? Alpha U by mu, correct?
Yes, sir.
And you know how to express this relation. So alpha was 1.22 lambda by A, U by mu. And it is similar to what we have obtained earlier, but the only difference is the mu has come in the denominator, right?
Mm, yes, sir.
1.22 lambda by A. And again, tan theta becomes A by 2U, 2U. Yeah. This is A. So U by A becomes how much? 1 by 2 tan theta, right? That's it.
Mhm.
Okay, anyway, we'll just put it A by 2 tan theta into 1 by mu. So you can see everything is there. Only mu will come as an extra element. So D minimum turns out to be 0.61 lambda by mu tan theta, which we can write as mu sine theta. And why we are trying to write this way, because mu sine theta having a very special meaning in world of optics. We call this as numerical aperture. And it is generally, in the when you go and buy a microscope, they will mention the NA, the numerical aperture value, in the on the box or somewhere. So it's like this value already. So because this is why it is required, because if you choose the lambda in the visible range, you exactly know what kind of a D minimum you can find. Okay.
Yes, sir.
So if they mention the numerical aperture, we know the D minimum in advance.
Okay, sir.
Understood?
Yes, sir.
So this is the formula of D minimum equals to 0.61 lambda by mu. You can see, depending on the question, if they give you geometry, you can add mu tan theta and so on. You can choose. You have to think that which one is better to get the answer. If they mention theta, and if it is easy to find theta in terms of tan, so okay, you can do it accordingly. All right, so these are some basic formula, and now time has come to solve some numerical problem. Okay. So, have I shared the wave optic sheet with you?
Sir, yes, sir.
Let me see if I can find some problem here.
Sir, you were also telling about the NCRT diffraction
Yeah.
problems.
Yeah. I'll go to the NCRT exemplar. In the NCRT, they haven't given any question, unfortunately. No, they have given something. Maybe one or two question. Let's see if we can find it. Open this text which I have shared with you. 10.14.
Yes, sir.
Yeah, try this question, 10.1. In static example.
Okay, sir. I think.
How much you getting?
Sir, I'm getting 60.
I think 60 is the right answer. Yeah. 30 is the right answer.
Sir, I applied tan theta formula instead of sin theta in the
Yeah, that's fine.
equation.
Yeah, that's fine. Question, yeah. So I think so, assuming human pupil have a radius of 0.25 centimeter and the comfortable viewing distance of 0.5 centimeter, the minimum separation between two objects of human can resolve at 500 nanometer wavelength. Okay. So the aperture size is how much? What is the aperture size?
Sir, that is only 25 centimeter, right, sir?
No, 0.25, 0.25.
Oh, sorry, 0.25. Yes, sir.
A is given 0.25.
Yes, sir.
Okay, anyway, we'll keep it. And the U is given 25.
Yes, sir.
What else? Mhm. Yeah. So tan theta will be how much? A by 2U,
Yes, sir.
0.25 by. It is both are in centimeter, right?
Yes, sir.
So I can write 2 into 25, which is 1 by 200, right?
Yes, sir.
And D minimum is how much? Formula.
Sir,
D minimum is
0.61 lambda by sin theta, which we could approximate to tan theta.
okay. So we can just write tan theta.
Okay, sir.
So 0.61 lambda is 500 nanometer upon 1 by 200. So it is into 200. So it's coming, no? How much?
Sir, 5 to it becomes 10 and we'll again get 60.
And oh, just a moment. A is given radius. It's
Oh,
radius, no?
right.
Right.
So we have to double that
Yeah.
value.
Yeah. So A by 2 means it's A by U now. 2 will not
Yes,
come.
sir. Yes, sir. Oh, then we'll get 30. Okay, sir.
Okay, everything is sorted now, right?
Yes, sir.
Fine. 30 micrometer. Whatever answer. 30 or 300, something like this. Huh?
Yes, sir.
Anything else?
Sir, I saw the exemplar question, and that is just the ratio of the
Yeah.
wavelength, right, sir?
Now do this question. I have shared another question. It's a JEE-Mains 2014 question.
Okay, sir.
2016 question. Question number 20. JEE 2016. So think about it, then we'll do it something else.
Okay. Sir, a
And
box
see,
of it
you
can
can
hold
see,
10 grams.
you can see that because there is no 1.22 involved, so you can take only lambda by for the minimum. Don't take 1.25.
Okay, sir.
Although it's not accurate, but you're not supposed to. I mean, you can understand that okay, what is the best way to approach because 1.22 will never come in the picture.
Yes, sir.
You said something.
Sir, no, sir. I was just confirming the question.
Yeah. Question one. Yes.
Okay, sir.
For question number 20, what you are supposed to do is assume the diffraction only from the edge of the slit. Okay. And assume the first minima at angle theta from the topmost edge. And then find the radius and try to maximize it using some formula. Okay.
Sir, they're asking like the minimum case.
Yeah, minima. Why maximum minima? So you just need to differentiate the function, right? If you can obtain a function, you can solve it. You can think this way. So the radius of this pinhole is given, right?
Yes, sir.
This is like opening. You can call the radius as A. So this is like a two-way. Okay. So when a parallel beam will come, what will happen? So if there is no diffraction, it would have come exactly like this, isn't it?
Right. Yes, sir.
But as a result of diffraction, the first minima will be at some angle theta. So what
Yes,
we do
sir.
is we take the central maximum as such, and then we take theta from here,
Okay, sir.
and then from here. So this is also theta. And now this new radius, we can determine using the function. Let's call this as Z, the separation. Okay. This is this separation
Yes,
as Z. So we know that if this is Z, this will be Z theta.
Yes, sir.
So this R will be how much? A plus Z theta. And theta we know is lambda by A, right?
Yes, sir.
R is how much? Now they're asking what value for A, R is minimum, right? So dr
Yes.
by dA equals to 0. I can differentiate.
Okay, sir. Yes, sir.
A turns out to be Z lambda. Okay, Z given here is L, I think. Okay. Now I recognize.
Yes, sir.
And since you got A equals to lambda L, so R equals to how much? Lambda L plus lambda L upon lambda, which is 2 lambda L. So R equals to 4 lambda L. Okay.
Okay, sir. Yes, sir.
Okay. So okay, this was the question. Now only one topic is left, that's called polarization. It is a small topic, so that I'll cover in the next lecture, and then after that we'll go back to modern physics. Okay.
Okay, sir. So,
Yeah.
sir, heat and thermodynamics, how long will it take to cover?
We can cover it. I mean, let's cover the heat and thermodynamics. Okay.
Okay, sir. Sir, because I feel like I need more clarity in that
Yeah,
topic.
yeah. So